Alright guys, welcome back to this series of Java Full Stack Made Easy. So in the last session we talked about the Java types of variables, and I told you in this video we will be talking about the Java data types. So in the last example we were discussing about the local instance and class variables. Let's now get started with the Java data types. So I'll just clean up everything that I have written here, and then we will go back to the main topic of today, which is Java's data type. Okay. So whenever I ask about the data types in Java to any engineering graduate, they generally tell me that it is primitive type and non-primitive type is what they generally say. So primitive type, and they call it as non-primitive. But I never agree to this particular definition, that is or a term called as non-primitive. If we take things in this context, in that case the world will have just two type of fruits. What is that? Mango and non-mango, right? And the world will have only two type of colors, black and non-black, right? So that is why I do not accept this particular term for the data types. Primitive types is fine, but the second type of data type is not a non-primitive. I don't know from where they get this word. Maybe some author might have written it as non-primitive, but Java sees it as class type data type. So there are two type of data types available in Java. One is primitive type, next one is the class type data type. So these are the two broader category of data types available in Java. So let us explore these two types of data types. Primitive types are what? They are simple values. Okay, so there are 8 primitive types available in Java, and in Java, apart from this primitive types, rest all are objects. Okay, so a class type are more complex objects, and including those objects that you create on your own. That means even a demo one can be a class type. We will talk about the class type later, but as for now, just understand that class types are what? They are objects. Primitive types are simple values. So the list of primitive data types available in Java are, and again there are 8 primitive types available. To remember it easily, you categorize it into 4 categories. Like you categorize into 4 categories of integral values, decimal values, character values, and boolean value. If you categorize this 8 into 4, it will be easy for you to remember the data types. So now when it comes to integral data type, it is byte, short, int, and long. So these 4 comes under the category integral, which stores pure numbers. Then comes the decimal values, float and double. So these are the 2 types available for decimal values. Now the next one is character, which stores one single character, and the last one is boolean, which can store either true or false. So now, considering these data types in Java, what for we have to pick up a data type? Because whenever we are creating variables, so what is a variable now? A variable is a name given to a memory. So whenever you are reserving a memory to store something, at that time we have to give the data type also. We have to mention what type of data will be stored into this memory. So when we say any of this, byte, short, int or long, it means that we are going to store pure integers. If we say anything of this, that is float or double, at that time we mean to store decimal values. If we want to store one single character, at that time we take it as character, and if we want to store true or false values, at that time we take boolean. Now the next question that comes up into our mind is, if we are storing pure integer values in all this 4, why do we need this 4? Why not just 1, right? Why not just byte, or why not just long? They differ in size. As a programmer, we should always be focusing on size, that is consuming less memory. So we have to always strive hard to utilize as less memory as possible and make our application as fast as possible. So that is why in all the cases we cannot go for long. Now what is the difference between them? Just the memory. Other than that, Nothing. All of them store pure integer value itself. So byte stores 8 bits of memory. Because of 8 bits itself, it is called as the byte. 8 bits makes up 1 byte, and then for short it is 16 bits memory, and similarly for int it is 32 bits memory, and for long it is 64 bits memory. So that way these things differ. Now let's go ahead and understand why should we pick up the data types accordingly, and what scenarios we will be picking up the data types. Okay, so first of all, what I will be doing is I'll be creating a byte type of variable, or else let's just consider that I have a variable of type integer and I want to store the age of a user. Okay, so when I'm storing a age of a user, obviously I know that the age will be in terms of numeric values, right? So now I'm considering this age in years. Okay, so age in years, when I think of an application development, if suppose I'm creating a banking application or maybe a gaming application, let's say let's take an example of a gaming application, and a user has to enter his age. Generally the people who play games, their age is between 14 to, let's say, somewhere around 40, right? So maybe there are some crazy people who play games at 50 also, right? So the range is around 14 to 50. Worst case scenarios, it can go to 80, right? Or in a very worst case scenario, it might go up to 90. After 90, nobody is going to play the games, right? So doctors will be playing games with their bodies, in fact. Okay, so now when I say the maximum value that I'm considering in this variable age is 90 or maybe 110, instead of declaring that as an integer, I should be declaring it as byte. Now let us understand why why this has to be declared as byte, and then how the data is stored in byte. Okay, so I can declare it as int age 110, or the best way is I can go for byte age equals to 1110. It can be the we are considering that as a maximum age of a user who is going to use our application, but byte can store up to 127. So I believe that if you're creating a gaming application, at that time age in years can be maximum 127. In fact, it will not be, but byte allows us to store the details up to 127. So the range of byte is from let's say 127 is stored in this, no problem. Let's just do a system.out.println and try to print that age and see whether 127 is stored or not. So when I run this, it says 127 is a valid value that can be stored into a byte type of variable. Now I'll just increase one number, that is 128. So when I say 128, here itself you will notice that it gives us an error. It says type mismatch cannot convert from int to byte. So any number that you have written up to 127 will be considered as a byte. If you write 128 here, it is considered as int because it goes beyond the capacity of that, and because of which we are unable to store the details here. Okay, but do not be confused, byte can store 128 also. Now how come it store 128? It can store 128 but a negative 128. Okay, minus 128, which is not equal to 128. So sometimes you might see in exams they might be storing it like 128, so that is wrong. 128 cannot be stored. If it is minus 128, yes, it can be stored. So let me save it and run this piece of code, and you will see that it can store minus 128. If I go beyond that range, that is minus 129, it cannot store. It goes beyond that. So from minus 128 till plus 127, byte can store the value. So our requirement maximum age is 110. So instead of storing it into an integer, we can store it into byte. By storing it into a byte variable, we basically save 3 blocks of memory. Each block is of 1 byte. So which means that we are storing what? 8 plus 8 plus 8. That is 24 bits of memory will be saved. Instead of taking int, if we take byte, we are saving 24 bits of memory. So let us first understand how the data is stored into byte, and then we will be able to understand why it can store maximum up to 127 and minimum up to 128 if we look at the way how the memory is stored. So let me just go back to my paint board and draw you a byte memory. So whenever I say something like this, what I've written here, I've written byte age equals to minus 128, or any value I'll write. First of all, byte age equals to, let's say I have written it as 12. Okay, and whenever we declare byte, so our compiler understands that a user needs 8 bit of memory which should store integer values, and for our machine it's all about zeros and ones. It cannot understand anything other than zeros and ones, right? So binary language is what it understands, the machine language. So now when the compiler is reserving 8 bits of memory for us, let's draw those 8 bits of memory. Okay, so when we are drawing that 8 bit of memory, we will also see how we perform the indexing from this, and I'll show you an easier way of converting your binary numbers into a decimal number and decimal number into a binary number. Okay, so this is 1 2 3 4 5 6 7 and 8. So the last index here would be 7 and the first index begins with 0. That's why the last index is going to be 7. So index 7, 6, 5, 4, 3, 2, 1 and 0. I hope that you know the basic rule of index positions and also the formula to calculate the values, which is 2 raised to the index position. Okay, so 2 raised to index position is the formula. So 2 raised to 0, anything raised to 0 is what? It is 1, right? So this will be 1. So 2 raised to 1, that is going to be 2. Okay, so this will be 2, and then 2 raised to 2, that's gonna be 4, and 2 raised to 3, that's gonna be 8. Okay, similarly this is going to be 16, and then this is going to be 32, this is going to be 64, and this will be 128. Okay, so whichever, this is how your 1 byte memory looks like. The capacity is up to 128 here, and if everything is 1, so it should be 128 plus 127, that should be 255, but the capacity of the byte is how much? Just 127, 127. That is because these are signed bits. So if you are taking a byte, the last index position, this position is reserved for the sign. Okay, last index or last bit is for sign, wherein what? 0 indicates a positive number and 1 indicates a negative number. So 0 is positive and 1 is negative number. So now if I have to store the least number, the minimum number here, so the minimum number has to be a negative number, right? And if I am storing a maximum number, the maximum number has to be a positive number there. Now, how does my memory store 12 in 12 will be stored in this byte? So wherever you can just add up 12. So 8 plus 4 is 12, right? So 8 plus 4, that is 12, and this will be 0 0. If I am not writing anything, consider it as 0. So the binary equivalent of 12 is 1100. That's what the binary equivalent. If suppose your byte age is declared something like this, age equals to, let's say 15 here, and if it is 15, again what we have to do is 8 plus 4, that is 12, plus 2, 14, plus 1, which is 15, right? So I have to just make it as 1 and this as 1. So the binary equivalent for 15 will be 1111. So that way we store the values into a byte. So I am talking about a byte. The same concept is used for short, int and long. Only difference will be what? The last index position will move to its last index position. For short, it will move to what? Short is 16 bits. The last index position will be 15, so it will move to 15. Okay, now if everything is 1 here, which will be a maximum number, right? So if everything is 1 and this is reserved for sign, so for sign what we are going to do is 0 indicates it's a positive number, right? So 0. And now let us count all of this. So when we count this, it is going to be 127. So how am I saying 127? The magic behind this number, you just see this. 2 plus 1 is 3 plus 1 is 4, right? 4 plus 2 plus 1 is 7 plus 1 is 8. 8 plus 4 plus 2 plus 1 is 15 plus 1 is 16. So that's how the numbers are arranged in the series. So 64 plus 32 plus 16, 8, 4, 2, 1. If everything is 1, we have to just go to the next number and minus 1. So that is 127 itself. So this is the maximum value which a byte can store. So this is how it looks like, and that is 127. I don't have an option to add another 1 anywhere. If I add a 1 here, at that time it is going to be a negative number, right? So let's add a negative number here and see what happens. So if this becomes minus, okay, increase the size of this rubber. All right. So let's talk about the least number. So when we talk about the least number, this should be 1. Rest all should be 0 because they should not be counted. So I'll just remove everything from here. If I'm not writing anything, consider that as 0. Okay. So let's clean up everything. So everything is 0. Now, if everything is 0, 1 is at only position what? 128. So we will be writing it as 128 here. But this 1 is at which position? The 7th position. Okay. So when it is at the 7th position, it is 1. So that means negative. So that is why your byte can store from minus 128 to 127. The same rule applies to all the other data types like short, int and long. So this way, this is how the data is stored into a byte. Okay. So I hope that is clear to you. So let me now go ahead and enhance this. First of all, I'll just copy this and put it into the repository for your reference. So let's go to the repository and create the new repository for this as day 3. So this will be day 3 slash demo 1. This is about what? Data types. And in data types, it is just about the byte type of data type that we are discussing. We have discussed about the primitive types, and one of the primitive type we are discussing, that is byte. So let's go back to our code and now try and take other type of data types. Now what I'm going to do is I have a byte type of data type here, and I'm trying to go ahead and create another int type of data type, and now I will say int I1 is equal to, so now it is an integer value. I can give anything beyond that 128. Okay, so this is fine because it's an integer value, can hold 200. It can even hold more than that. Okay, it can hold up to what? 2 raised to 31, right? All ones there, all ones. And the last position, 31st position will be 0, rest all will be 1. So you calculate that, and that will be the maximum range of integer. Now what I will do is, when I have this byte and int, I will try to also do something like this. That means I want to perform a typecasting. Typecasting means conversion of type from one type to another type. Suppose if I'm taking this as an example, and here I try to change the value of that I1, something like this. If I say I1 equals to age, so at that time the value of I1 should be whatever is in age, right? So let us print this I1 and see whether we get the third result as 120 minus 128 or not. So let's run this, and the third result is minus 128. So this is completely valid, this is completely fine. Okay, so what I'm doing is I'll just erase this and take it in simple terms. If I have a byte variable, byte a equals to let's say 90, and then I have an int b variable which will be storing a. So there are two type of conversion that is happening, that happens in Java. One is implicit and another one is explicit. So I'm just going to check what is there in this variable b. If I save it, I'm expecting this should contain 90. So when I run it, it is all fine. Similarly, what I will do now is I will try to take an int variable. Let's say int variable c equals to let's say it is 80, and then byte variable d equals to c. So first of all, the question is, can byte d store 80 or not? Yes, it can store the value 80, but still I'm getting an error here saying that it cannot hold c because there is a chance of loss of data. So if I put my cursor here, let's see what is the error. The error says type mismatch cannot convert from int to byte, but here byte to int is converted, here int to byte is not being converted. So here also typecasting is happening. It is implicit typecast, and here an explicit typecast is required. So when is this explicit typecast required? Explicit typecast will be required when there is a chance of loss of data. So here there is a chance of loss of data. Now what do I mean by chance of loss of data? We will see that in detail. First of all, let us just give an explicit cast and understand this. So I am saying byte, and then after that I will try to print the value of d. So value of d is the value of c, which is nothing but 80. So that's what I'm expecting here. 80 should be printed, and here 90 should be printed. So let's run this piece of code and see that yes, 80 is being printed. It's completely fine. So now explicit casting will be required when there is a chance of loss of data. So in what case there will be a chance of loss of data? Let us understand that. Now in case if I have an integer e equals to 200, okay, and then I have a byte f is equal to e. So when I'm trying to do this, at that time once again it is asking me for casting. So when I perform a casting, now again there is a chance of loss of data. Now that is because, see, int can hold 200, value 200, it is completely fine. But what is the capacity of byte? The capacity of byte which we have discussed is what? 127, positive 127 and negative 128. So byte cannot store 200. Now what will be the result now, since it goes beyond its capacity, right? So let's see what is going to be the result for this. So I'm trying to print f. I was expecting f to hold 200. I also know that f cannot hold 200. Let's see what is the value stored into f. So when I run this, it says it is minus 56, which is being stored here. So explicit cast, there is a one limitation of explicit cast, that is chance of loss of data. So whenever there is a chance of loss of data, compiler is going to ask you for an explicit cast, which is also called as the programmer's cast, and this implicit cast is also called as the compiler cast. So let us now understand how exactly the things are happening with very simple example. So once again I'll go back to my paint board and make you understand what is happening. So before we directly dive into the memory architecture of byte and int, let me give you a very simple example. Let's say we have two water bottles itself, okay. So there are two water bottles, one is of 1 liter, another one is of 2 liters. That's what we are considering here. So now we have two water bottles, one is of 1 liter, another one is of 2 liter. So this is one water bottle that we have, this is the other one which we have. So let's also, just for the understanding, let's write it as 1 LTR, okay, so that we know that the capacity is 1 liter, 2 LTR. Now if suppose this water bottle is full, okay, and I'm trying to pour the content of this water bottle into this water bottle, is there any chance of loss of data? No, right? There is no chance of loss of data because 2 liter can easily hold 1 liter water. So that is what is happening in our first scenario. Byte is of 8 bits, right? 8 bits of memory is being stored into how much? 32 bits of memory. So from smaller to higher, it is implicit cast. There is no chance of loss of data, so casting is happening automatically. Fine. So this is what has happened in the first case. Suppose if I do a vice versa case like this water bottle is full, it can even be at 1.5 liters. So now I take this data and pour it into 1 liter bottle. So what will happen? This will hold 1 liter water, and the other liter, one more liter of water will be flown out. So there is a chance of loss of data. In all the cases, this will not be full, right? So there is a possibility that this can hold the water up to this itself, or it can hold the water up to this itself, right? So we as a programmer, we should be knowing what is the value. We are concerned about the values, but compiler is concerned about the size itself. So that is why even when we had a lesser value here, so you can see that even we had a lesser value, that is 80, which can be stored into byte, compiler still asked us to perform an explicit cast, because compiler is saying what? Compiler is saying int and byte. Compiler is not saying this 80. Compiler says, okay, somebody is trying to convert an integer which is 32 bit into 8 bits, so a programmer has to give a confirmation for that. Okay, and in this case it is full, you can consider. So in the previous case it was this, but still the compiler says you are trying to pour the content of a higher value into a lower value, and explicit cast is required. And in the next case it is full, like up to here. And when I pour this, so there is a chance of loss of data. Maybe this is 1.5. okay, so in 1.5 what happens is 1 liter will be stored, 0.5 will be lost. So again it is asking you for a programmer's cast, that is explicit casting is required. So I hope by this example it is clear to you, whenever a lower value is converted into higher value, that is explicit cast, and a higher value getting converted into a lower value always requires an explicit cast, because there is a chance of loss of data. So whenever there is a chance of loss of data, explicit cast will be required. Now going back to why we got this result 50 minus 56, what about the data, what about the result, why is this we are getting as minus 56? So let us understand why we got that minus 56. It's not a random value that we are getting a cut shorted memory of int. So let us see that again with the memory architecture here. So I hope this particular diagram was completely clear to you. If you have understood this, then understanding the result of minus 56 would be far more easier for you. So let's go ahead and understand that. Now what I will do is, we have this let's go for a new paint board and draw it once again. So what we have is, we basically have created an integer variable. Okay, some name is given to it, maybe E and F. Yeah, E is given. So E equals to 200 is what I have given. And then what I'm trying to do is, I'm trying to do something like byte F equals to E is something which I'm trying to do. And also because it requires an explicit cast, I've done an explicit cast also. So let's understand this in terms of a memory architecture, how 200 is stored in integer and how that can be stored into byte. So integer, we know that it has 4 memory blocks. So let's draw that. Block 1, block 2, each block is of 1 byte. Okay, so that means 8 bits. So 3, and this is the 4th block which I am more concerned about. Okay, and we have already discussed in the previous diagram about this byte data. Here we have 128, then we have 64, then we have 32, then we have 16, 8, 4, 2 and 1. So these are the values which are stored in there. Okay, so if I try to store a maximum number in a byte, we know that it is 127 and minus 128 is the minimum number. Now since this diagram is for integer, okay, 4 bytes of memory, this is for integer. So the bit that will be reserved to store the sign will be this, the last one. Okay, so which will be what? 31 in our case. So 31 position, we have a positive number 200, right? So 0 or 1 will be stored here at this position. Now what is being stored? 200 is being stored. So let us see how can we store 200 into an int memory. Byte memory cannot store 200, but int can store 200. So let us understand that. Now I will take the maximum number from here and add it to the next maximum number, that is, I will say 128, okay, plus 64. So 128 plus 64 is what? 192. Now I will do 192, 8 remains, I'll just add 1 here, so that will be 200. If you see the binary value like this, if it is an integer, okay, 1 1 0 0 1 0 0, that is 200 in int. Okay, that's 200 into int. This is what? 1 1 0 0 1 0 0 another 0. Okay, so that's what we store into an int. Now, how is this same thing stored into a byte is our concern. So this was the data that was stored into int. So what happens is this will pick up only this particular part, okay, byte, because cut short this 4 bytes of memory into just 1 byte of memory. So this is the memory that remains, okay. So I will draw the remaining memory here now. So the remaining memory is this, and once again I'll write 128, then 64, then 32, 16, 8, 4, 2, 1. Okay, so 200 was stored into int that way, and now we are cut shorting that same thing in here. So this 0 will be gone, this empty, all zeros will be gone, this will be gone, only this remains. So what remains is here 1, and then 1 here again, that is 128 plus 64, 92, and 1 here at the position 8. This 32 position will be 0, and if I'm not writing anything, consider that as 0. Okay, 8, 4, 2, 1. So this is basically what 11001000. Now this is a byte memory. Okay, byte contains this now. So byte f should be pointing to this memory. So when byte f is pointing to this memory, it is byte, right? For byte, this particular bit is reserved for the sign. So this has to be minus, right? Now minus 1, because it is 1, right? 1 means minus, and this is 128. So it will be minus 128. Okay, and then plus, what is this? 64. So minus 128 plus 64 plus what? 8. Okay, plus 8. Now what we will do is we will just simply calculate these things. So live that minus 128. What you do is you do a 64 plus 8, that is 72, right? Now minus 128 plus 72, right? Minus 128 plus 72, you can calculate that, and that is going to give you the result as minus 56. So if you go back to your program, that's your result, minus 56. So this is what is happening internally when you try to convert an int into byte. All these blocks will be gone, only what is remained in this byte will be taken. You can take another example for this and calculate it accordingly and check whether you're getting the exact same result or not. So what you can do is you can simply, after this 128 there is 256, right? So what I will do is I will say int will be holding 256. What I will try is I'll try like int e will be equals to 256. When it is 256, we write 1 here, rest all will be 0, right? So let's go ahead and write that. So e will be 256, rest all is 0. Now we are trying to print f, and if all of that is 0, 0 is positive number and rest all is 0. If it is 0, we don't calculate anything, right? So let's run this and see, we are expecting that to be 0 and the result is 0 itself. So this is how the memory works with typecasting, and this is how typecasting basically works on memory, not on value. So I'll put this example once again into the repository. So let me copy this and let's go to the repository and create another file, call it as demo2. Okay, and this is typecasting. Okay, demo2 typecasting. All right, so see, sometimes the videos can be lengthy, but I'm trying to start it right from the scratch and explain you the details. Obviously, as I told you in the previous video, learning Java maybe in 1 hour or 30 minutes and all is a myth. So until and unless you dive deep into Java, you won't be able to understand the advanced concept of Java. So I hope this is clear how a byte and int is working, what is the memory architecture which is working behind this, and also how typecasting works, what is implicit typecast and what is explicit typecast. Now let's go ahead. In fact, what you do is you are performing typecasting in Java without even your knowledge. So you might have definitely done typecasting before. So where do you do typecasting? Let me give you one simple example where you are performing typecasting, but you yourself don't know that you are doing a typecasting there. So let me give you an example for that. So generally, maybe it's whether in Java or in C++, we follow this float. Suppose if I'm writing float a equals to 10.5 and just writing it as 10.5 would give me an error. So you can notice that it is 10.5. It is giving us an error. So you generally tend to write it as f, right? And it will work perfectly fine. So why are you actually writing that f? What is the story behind that? So let us understand it. So to understand that, you need to remember one point. Compiler reads all decimal values as double by default. So this value, whenever you write 10.5, it is double by default. So because it is double is a higher value. It has more memory than float. So from higher to lower, it requires an explicit cast. That's what we have learned in the previous example. So if that is the case, can I write something like this? Float b equals to 10.5. Instead of typecasting it with f, can I typecast it to float? Because I told you it is just a typecasting itself. So writing float is also valid. So this line and this line of code are same itself. So this is also typecasting, and writing f is also typecasting. So you can either suffix it with float or prefix it with f, because compiler is reading a double value by default. For example, if I create a double variable, double d equals to 10.5 here, so there is no problem because it is double value being stored into double. And if I try to store that float, maybe let's say f equals to d, this will not be possible, because like we did in the previous example, byte b equals to int x, we cannot do that, right? So int is higher value, cannot be stored into byte without an explicit typecasting. So here also, without an explicit typecasting, it cannot be done. Okay, it cannot be done. So that's why we are performing a typecasting. Since values here automatically understands, the compiler can understand f cannot be stored into a decimal value, right? So a programmer's intention is to perform a typecast. So which line looks easy here? Instead of writing float like this, easier one is f. So because of that easier approach, everybody is following this concept of suffixing a decimal value with f to convert it into a float. Okay, so it's not a rule. Okay, it's not just a rule. Sometimes in your colleges they might have told you, for float value you have to write f, means you have to write f. It's not like that. Why are you writing that f? That is because you are typecasting a double value into a float value. A double value is higher than float, that's why you have to typecast it. Choice is yours whether you want to typecast it this way or this way. So because this is an easier way, everybody has opted for that way itself. So whatever you print, whether you print a now, it will give you 10.5. if you print b, it will give you 10.5. if you print f also, it will give you 10.5. so let's print all of that. So I'm printing a, b and f. So all of that is 10.5, so it should give me 10.5 as the result. So this is how you are performing typecasting in there. So I'll just copy this, and once again I'll put this into the repository. So this is our demo 3, typecasting float. Okay, conversion of a double value to a float value. So let's just commit this. All right, so now coming to the other two primitive types. So we have basically discussed this 4. You can also write the other values. You can test the other values like a long value or a short value and all that. You can test on your own. One important point about the long value I'll tell you. Let's erase that. So if suppose I have something like long, I have declared a value long, let's say L equals to, and the 99, 88, 77, 66, 55, 44, this can be stored into a long variable. It is in its capacity itself 64 bits, but I'm getting an error here. So when I put my cursor here, it is telling me that what you are writing is int, but you are trying to store it into long. Int literals cannot be stored into long. So why is this? That's because by default, like compiler was reading your double decimal value as double by default. here compiler is reading this numeric value as int. It's not always int by default, because in a previous example we have seen when we were writing byte x is equal to 90, it was not int at that time, it was considered as byte itself. So now it is considered as int. So what we have to do is we have to typecast this value into long, right? So we know that typecasting can be done this way, right? Or there is another way of performing typecasting. What is that? So when I try to do this with just a value, it's not valid. So if it is just a value, then we perform something like this. Either a capital L or this will be completely valid. So if it is a variable, then we can simply do a typecasting by converting it into a long. Basically, we don't need to typecast anything to long, because that is the longest value available for us. So that's how we perform again a typecasting, and generally to differentiate we write as a capital L there. So let's save it and run this, and you get the long value now. So to store long values, you have to always mention this here. So let me save it, copy and put it into the repository as well. So this is my demo for long value. Okay, long data type, you can say that. All right, so heading forward with the character now. So what are the character type of data, which what are the characters that can be stored into a character? See, whenever you are storing a character, it means that you can store one single character into it. That means you can store a, you can store 1, you can store any special case character. So it can store your alphabets, it can store numbers, it can store special symbols, but it has to be just one single thing, only one, not more than one. So let's go ahead and understand that. So when I take a char x is equal to, so I can store anything here, I can store a here, but I cannot store something like a and b together, because these are two different characters. Okay, I cannot store two same characters also. It cannot be more than one character. Okay, it has to be one single character. System.out.println, and if I print x, save it and run. So when I save it and run, we get the value of that character a. It can store alphabets, it can store numbers as well. So we get that character. So this is character 3, not a number 3. There is a difference between having a character 3 and a number 3. As the time progresses, you will understand that as well. So then I have the ampersand stored into a character, and then I run it. So an ampersand is printed. So characters can store special characters, it can store alphabets, it can store numbers, but the requirement is that there should be only one single character to be stored into it. Okay, now in some of the interview questions and all, or maybe when you are attending a Java exam, Java vendor exam like OCJP or OCJA, at that time they might confuse you with something like this: char y is equal to 65. Now how many characters? 6 and 5, two different characters, right? So whether it is valid or not. So in this example which I have written, it is completely valid because compiler is not giving me an error here. So when I write y, what I'm expecting is, I'm expecting this y to be storing 65. But when I run this, you see the result is different. So when I run it, the result is a, which is an ASCII equivalent of 65. So characters can store this byte. Here 65 is considered as a byte value. So character is of 2 bytes, byte is of 1 byte. Automatically the conversion has happened. So this is what an implicit cast is happening here. Okay. Implicit cast is happening here from what? From byte to char, because byte is of 1 byte, character is of 2 bytes. So that's what is happening. That's why it is valid. And if they write it something like int, let's say z is equal to 65, this is invalid. So they might trick you about the single quotes here. So do not be tricked on that. Know that if it is written like this without the single quotes, it is 65 byte gets converted into a character, automatically implicit casting will happen, and in that case an ASCII equivalent character will be stored, not this number. Okay, so then this is completely invalid. When you are storing a character can take only one single value. Do remember that particular point. So I will copy this and put it into the repository as well for you for character. Demo 5 char. And the last primitive type is boolean, which can either store true or it can store false. In Java, character is of 2 bytes, whereas in C++ and all, character is of 1 single byte. In our next video, we will see that in details about the character being of 2 characters. Okay, now let's talk about a simple boolean value. A boolean x can either store false, okay, or it can store true. System.out.println x. So either a false value or a true value. Size is just 1 bit, not byte, just 1 bit. Okay, so here we go. It can store either true or false, and if you write it in double quotes, it is invalid. It is considered as a string. If you write it in single quote, it is considered as a char. That will also be invalid. Okay, sometimes again in Java exams and all, they will try to trick you with this. Although the value true is valid for boolean, but because it is written as a string cannot be casted to boolean this way. Okay, so I'll just remove this. This is a valid thing. So we talked about what the primitive types, which are simple values and categorized into 4 categories: byte, short, int, long, float and double. Byte, short, int and long can store only pure numbers. Float and double can store decimal values. Character can store 1 single character. It can be anything, an alphanumeric number, alphanumeric character, or it can also store what? It can store the special symbols, but it should be 1 single. Boolean can store either true or false. So size of byte, short, int, long we have discussed. Float and double. Then char is of 2 bytes. Boolean is of 1 single bit. So primitive types are simple values. Apart from this primitive types, rest all thing in Java is class type itself. Class types are objects, even including those that you declare on your own. So I'll just copy this into the repository and put it here, and the other things we will talk in our next video. Fine. So this is our demo 6, which is character type of data type. So a lot more things we will do with this continuation of this character. We'll try to they have already converted a char into int. I will explain you about why this character in Java is of 2 bytes, why not just 1 byte. Okay, so I hope you have understood this, and if you have any questions, you can ask the question into the comment section. And if you like in the series, please share the series with your friends and subscribe to my channel. Have a good day. See you in the next video.